So, good morning, ladies and gentlemen. I will welcome you to this Living Lab lecture series. Today we will talk about security research here at the ScaDS.AI, and our specific topic is the intrusion detection. My name is Jörn Hoffmann, and I will host this session together with my co-host Martin Grimmer. Hello. Hello. So, what it is all about? If you consider this meme here, you will see that we spend a lot of money for the cybersecurity these days, and it is subverted through easy things like to open up an email attachment. And that's exactly what we want to prevent with the intrusion detection system, or to detect with the intrusion detection system, to identify an attack on a computer system. So a short outline, what we will present today is just a short motivation about intrusion detection system, why it is important. Then we will go into the basics of intrusion detection and how we collect data. Then we will talk, or Martin will talk about the example algorithms and the Leipzig intrusion data set. And at the end, there will be a short conclusion about the information you heard in this lecture. If you consider the upcoming scenarios and threats in the IT security considered in the companies, you will see that these that ransomware attacks here on the top are very threatening for the participants. About 90% or rather threatening, so it's very important to cover them. Also, zero-day exploits, spyware attacks, backdoors and trapdoors, and so on. What we can do with the intrusion detection here is we can detect with the host intrusion detection system ransomware, zero-day exploits, spyware, backdoors, and trapdoors, and also tappings into computer, e.g. via email or other malware, for example, to mine cryptocurrency and so on. And these are major threats we want to identify, and then in the second row, then to prevent. Okay, what is intrusion detection? Intrusion detection is the monitoring of a system, or network system, or host system in our case, for malicious activity. So activity which is hidden for the user. The basic principle is for an intrusion detection system to collect some kind of data, then scan this data for malicious activity, and then if there is an attack, if there is some of this activity, then trigger an alarm or alarms. Intrusion detection cannot prevent an attack. It can only detect it after it happens. So it's a reactive method. And it is comparable to a virus scanner or a malware scanner these days. Nowadays, there are established different kinds of intrusion detection systems. One is the network intrusion detection system, which is a centralized system, which is in a network component like a router or a switch or a bridge or something like that. And it observes the network packets, the network traffic between the computer systems. On the other hand, we have the host-based intrusion detection system, our HIT. It is inside a physical host or inside a virtual machine, or observes a physical host or observes from the outside the virtual machine in our case. And so it can collect much more data, not just only network packages. And this is our main aim in research. So the sensors here, the virtualization, the fast acquisition of sensor data, and the real-time analysis of the data. Further on, what is our data? Our data are system calls. System calls, you have to consider that modern computer systems are divided in two parts. We have this application or the user mode, and we have the kernel mode below that. The applications usually run in application mode, and the kernel or the operating or large parts of the operating systems like the drivers and so on runs inside the kernel space, and this kernel manages the resources. If an application wants to access some files or Ethernet or network sockets, or want to share resources or gather resources or free resources, it calls the kernel via a special function call, via a system call, e.g. to create, task, open, and read files. And we use this interface, this call site here, or this call information, the system call information, to get a footprint of the application. We consider the system call number, the call and return parameters, the thread ID, and other metadata. Here's an example. We see this is a timestamp. This is the task ID, and you see there's an Apache 2 server application is running, which calls the select system call, which means wait on data. Then there's another thread which epols the data, and then the select here from the other from our original thread returns with some result. So that is our data, and now we want to analyze this data. There are two principles of work how to analyze in the global space this data. The first principle is simple pattern matching. So we search for a given pattern which is in a database, like a virus scanner, e.g. For program states, open, close, hashes of memory, or hashes of, in our case, for system call parameters, or for file I/O patterns, read, close, open, something like that in this sequence. And our detection rate in this case, in the pattern matching case, is determined by the patterns given by the database. And that is the reason why virus scanners, also malware scanners, continuously update their internal databases. But what they cannot do is detect unknown behavior, so behavior which is not in this database. On the other side, they have a high accuracy to find the data, and it's very a fast approach. We've chosen the other side around, which is called anomaly detection. In anomaly detection, we classify some behavior, some sequences as normal, and detect derivations which are outside of our cluster, of our class. It's determined here on the right side with the red dots. Anomaly detection-based systems usually have also a high detection rate. They can detect new attacks, but they usually suffer from false alarms. And this is our main aim in our research, to lower this false alarm rate. So to get in touch, what is the challenge behind to lower the false attacks rate? We have a simple example here. Now we don't want to consider the system calls. We make it a little bit more picturesque with muffins. We learn our normal behavior, which may be an application like Apache accesses files, and so that it's normal behavior. It's a muffin. And here on the right side, you see our test data. We have different kinds of these sand muffins here. And we learn the normal behavior. So this dog here is not normal behavior. Also this orange or sand colored. And we can now learn our normal behavior. But then there comes up a question, is this correct? No, it's not. We have this dark chocolate muffin, which is outside our normal behavior. Usually we detect this as false positive, so it's detected as an intrusion, but it's not, because it's a muffin. And we have also attackers. In this case, this muffin dodge dog here. Thanks to the Photoshop skills of Martin, we have combined them. You see, it's falsely detected as correct, but it's a so-called mimicry attack. So this is a false negative. Here we want to attack. In the real sense, we don't learn muffins, we learn the behavior, so the system call sequences or frequencies of these system calls, and we want to analyze or we analyze them to identify the different kinds of attacks. Okay, how it's done? With my co-host Martin now will talk about the algorithms and the data set. So Martin, thank you.
Hello, my name is Martin Grimmer, and I will continue this talk here. And I will introduce you to one of many possible algorithms for intrusion detection. And for this lecture, we choose the system call graphs algorithm. The task here is to build a graph from the system call sequence to identify intrusions. And here we use the concept of n-grams, which are short subsequences within this given sequence. And for simplicity, we use just numbers instead of system call names here. So we want to build a graph from this training data. And we just use the first n-gram in the sequence and create a node in the graph from it. And we just call it as a n-gram, in this case 1, 2. Then we go to the next possible n-gram in the sequence. This is here the 2, 3. Build again a node from it. And in addition, we add a directed edge to the graph. And this procedure will be repeated until we are done with the whole training sequence. In the end, we have a more or less complex graph, and we use the transition probabilities as edge weights. This looks like this. And now we have simply a Markov chain of nth order, and we can use this to detect intrusions by just do lookups in the corresponding transition probability table. This is a lookup table where each transition from this graph is mapped to its probability. So if we have some test data here, we want to give a subsequence of length 10 here, from here to here, one anomaly score, which we can use to differ between anomalies and normal behavior. The first step is to ask, is this transition from 1, 2 and to 2, 3 within the system call graph or in this table? In this case, this is true, and we simply note its transition probability. Then we move to the next transition here in the sequence, look it up, and note its probability. And we do this for all other transitions in this test data until we reach a transition we do not have in this graph, and we call this mismatch. So this mismatch has a probability of 0, and we just note 0 here. We do this for the rest of the subsequence, and then we can finally calculate the anomaly score here, as you can see. With this anomaly score, we can then slide the whole window from the top here one position further and repeat this process. And if we do this for a whole a lot of system calls, this can look like this picture here. We have a brute force attack on a given computer system, and we plotted the anomaly scores over time. And as you can see, we have at some time here a really high anomaly score in comparison to the normal behavior before. And the intrusion detection system can then alert the administrator, the IT security guy in your company or something like that, if the anomaly score is higher than a given threshold. That's I think all I can do to introduce you a simple algorithm here. But we have many other algorithms in our toolbox. As you can see here, we have a comparison about from 7 other algorithms over one of our data sets. And I want to show you here the green is a system call graph algorithm, and it can detect up to 89% of all attacks from this data set, and does on average 29 false alarms, which is more or less okay. It depends on the use case, I would say. And in addition to this algorithms here, we have evaluations of different other algorithms like long short-term memory networks, self-organizing maps, transformer-based architectures, and so on. And the takeaway here is that artificial neural networks mostly do less false alarms. As you can see here, one autoencoder architecture we tested has only 2.2 false alarms on average, but they are slow in comparison to the classical algorithms as you saw earlier here. And on the other hand, the classical algorithms have a higher detection rate. So it's not easy to decide which algorithm is best suited for a real-world use case, because no one wants many false alarms, because each false alarm has to be investigated manually. On the other hand, you don't want to miss an attack. So our goal here is to find a suitable combination, maybe of different algorithms, or a completely new one which has the pros from the classical algorithms and the artificial neural networks. So I mentioned the data set earlier. The problem was in the last years there wasn't really a good data set for this kind of research, because there were some data sets available here, but they are either outdated, as you can see from the dates. They were too simple, haven't got any metadata, no arguments of system calls or return values, and so on. Therefore, we published our own data sets in 2019 and this year. And these data sets look more or less like this on the bottom here. You have timestamps, user ID, process IDs, and so on. You have all the metadata available here. We can even look into the data buffers of different system calls here. And here on the side, we have an overview of the size of these data sets. We have different scenarios there named after the security incident or the common vulnerability enumeration number here. For example, this is a infamous heartbleed bug. And I hope that this data set can help us and other researchers to enhance the research here.
So this was it for our short presentation and our research in the intrusion detection, our security research. To wrap up the lecture today, we have introduced the basics. So what is the intrusion detection? It is a reactive system to reveal an attack after it happens. We have this divided into anomaly-based and systems and the pattern matching systems. And the anomaly-based systems, the one we use here, can detect unknown attacks. And our approach, we use a host-based virtualized intrusion detection system with anomaly detection algorithms. The system has a high detection rate and a low false positive rate. And as data source, we use our system called information. For our methods, here we have presented a simple algorithm with the intrusion detection with the call graphs, but we also use other algorithms like the artificial machine learning algorithms to compute an anomaly score, and we have built up an intrusion detection data set which you can use for your own experiments. So then we like to thank you for your attention, and we are here for your questions. So, thank you.